Hello all. I am Samuel Cortez and I am working for the Supercomputing Core Labs. In the following 25 minutes, I will attempt to make you understand what really makes a container. First we will see what the benefit of using them is. Then I would like to make you touch a little bit more about their intimacy. How we came up with this solution, why it has been so appealing. Containers means Docker in the mind of most of us. I will tell you more and up to what extent this implementation is pertinent. In the end of my talk, before leaving the floor to Mohsin, I will explain you why we could not use Docker out of the box on our HPC shared system, and what is usable as for now. To set the scene, let me briefly demonstrate the power of containers. First let me ask you the following. How many times have you had to install a given piece of software in the past? Whether it was an application or a simple library. How many minutes have you had to struggle before setting up finally your working environment and actually start your real work? For me, I have stopped counting. For example, in the case of LAMP, providing a database, a web server and a PHP environment to start coding, even if I surely already did it hundreds of times, it's still not instantaneous at all. Hopefully one of the best solution came from a software environment whose name was chosen after this giant metallic boxes that revolutionized world trade exchanges 10 years ago. The containers, as they are called, indeed offer an excellent way to package, transport, deploy, combine and track a software environment. Let me make you a demo to convince you fully. On my Linux workstation, let me install a complete LAMP environment right before your eyes in less than 40 seconds. Only 2 Docker commands are required to do the job. The first one installs a MySQL database using a MariaDB container image. When issuing this command, the image is downloaded from the Docker Hub repository, if it is not already present on the current file system. Once downloaded, this image is used to instantiate a container starting immediately a database server on my machine. The second command provides a full PHP web environment with the Apache server included. Once downloaded, this container runs the web server that allowed to test any PHP website. Et voila! No compilation, no unzip, no complicated configuration files to fill up. All as a matter of choosing the container images and setting some environment variables to configure them. So let's understand now how a containers works. Up to Docker documentation, a container is a standardized unit of software. More precisely, container can be seen as only isolated groups of processes running on a single host, which fulfill a set of common features. And that's exactly why it is so pertinent when it comes to deliver an application environment. As it is isolated and bundle both processes and feature, it's a unique way to transport conveniently a whole environment from a machine to another. It is also a very light way to do so compared to what is known as a virtual machine that could cover the same purpose. For now, let's not dive in the difference between virtual machine and containers. But I would like to make you feel how a container works thanks to an allegory. For me, containers environment indeed appear as the ideal gathering of these 4 objects. But give me a minute to explain further and you will see it makes some sense. Because when you think of it, container technology is all about deploying an environment by masking current resource and replacing them by other when seen from the inside of a container. Detailing exactly how to build and reproduce an environment. Make available this environment as images and building recipes, saved in a repository where it can be downloaded. And run on another infrastructure that have everything in place to receive and start the image. Before getting more into details, let me just briefly point some important architecture design when it comes to OS. The key thing to understand is that an operating system or OS is composed of several software layers more or less close to the hardware. From these complicated diagrams showing the typical software environment put in place by an operating system, let me just point two different zones and you will see my point. The first one is the zone in red, covering the hardware of a system, and the kernel software layer. The kernel is the lowest level layer of an operating system. It is intimately in relation with the hardware of the machine it's running on and furnish a system interface for the application to interact with the resources. In the kernel, you will find the whole machinery to orchestrate the processes, communicate with the hardware peripheral, and prioritize tasks. Kernel is a very low level, and the crucial component of the operating system. The other layer is all the rest. It's called the user layer where the applications, the process are running. So here's the thing. A kernel is so close to the hardware, so deep, so imbricated, that if it need to be changed, patched, amended it usually requires to reboot the whole machine. At the opposite, everything in the green zone can be modified, appended, enriched more easily. And every container-related operation will occur in this green zone. To my knowledge, a container cannot, absolutely cannot, change anything in the kernel zone. So now, how shall we cope with that? Let's look closer to one application. On a given machine, an application can be seen as composed of two things. First, some time allocated by the kernel scheduler to run or execute some code instructions. And second, all the resources either used or produced by this running application. It can be memory, files stored on the disk, either libraries or data, use of specific command of one's system. And it's exactly with these resources that a container is playing. To understand what different perspective the container brings, let's examine the classical way we used to install applications. It can be done either from a package to install, and it usually requires administrator privileges. Or it can be built from scratch directly from the sources and using a compiler. For the first method, installing from a package, it goes that way, assuming that you have root privileges. First, the package compatible with the current version of your OS is downloaded from a repository. Then it is uncompressed and the files it contains are added to the files already existing. Eventually some configuration file is either added or modified on the system. When installing from sources, it is almost the same, but it can be done as a regular user most of the time. You need to download the sources and uncompress them. Then comes the compiling step that can be tricky, as you need to be sure all required dependencies are installed and link correctly with them. The produced are then to deployed on the file system, and made available to end users. Not only can it be a time-consuming and challenging process when it comes to be compatible with already installed dependencies, but it has also two major issues. First, the package has either to exist in the distribution of your OS and be compatible with software already installed. This is usually the case for major application, but bundling your software is also time-consuming. Second, how to solve the issue of having to install two applications with antagonist dependencies. That's where container approach provide a very elegant solution. In the classical installation procedure, deployment occurred via the addition of files or configuration setting to the current resources. But containers also allow us to mask things. Let me show you how it goes and demonstrate how powerful it is. On the left side of the slide, I portrayed the current environment, as seen when logged simply on the machine. Here is the complete file system, for example. Now let's see how it looks from inside a given container, shown here on the right side. You see the trick. The complete file system has been changed. It is overloaded by the own file system that is embedded inside the container. And that's the whole thing. And masking, though simple, is a very powerful feature indeed. Because, let us point one very important detail. The container runs on the same kernel as every process on the system. It is just a process running in a specific environment with modified, patched resources. And it is so powerful. because by masking, we can run in an entirely different context, even changing a whole Linux distribution. Here, for example, whereas the OS is Red Hat, we run Ubuntu inside the container. Yes, we do run a complete and fully operational Ubuntu distribution. It makes sense actually. Because when you think of it, a Linux distribution is composed of a kernel to boot and a set of file to install that will form the low-level commands of the file system. So, as long as they run on the same kernel, two different Linux distributions can easily live together. The beauty of it is that this masking occurs per container. So nothing prevents to run several of those with each a different Linux version. And as they are regular process with a modified access to resource, their performance does not suffer from any important overhead. Let's add that the containerization usually impacts a set of processes. It is a whole and coherent environment that can then be deployed. Let's examine how this masking feature applies to other resources of the OS. Processes, for example. Here also, it is very simple to understand. Whereas your current OS runs hundreds of different Unix processes, inside a container, you will only see yours. You experience here the concept of isolation of your deployed environment. That way, when living from inside a container, you minimize all side effect related to the specificity of the hosting OS. Here, though, the processes running inside the container are accessible from the outside. Yes, again, a process running inside a container is a regular process. If you are attentive, you have surely noticed a surprising fact here that could cause us trouble. We will get back to this later on. And the idea is the same with network interfaces. Whatever they are on the hosting OS, you can filter them in your container. Make appear only one interface, for example. And the isolation is both way here. Because outside the container, no process has access to this new interface ETH2. If needed, one can choose to publish it outside of the container though. Here, ETH2 will be seen as ETH3 in the hosting OS. We can also map this interface to an existing one. Or we can decide to have our own private network, only seen from a set of containers. You realize how convenient it is to deploy not only one, but several applications working all together. And the containers, and the private network spanned within them, can of course be spawned on different machines. Same can be done with network ports. On Docker, for example, if a container spawns a database, by default, this port will only be reachable from inside the container. If needed, one can easily map it to the outside of the container, adding this parameter at the launch time. Notice how it works. As it is a port mapping, we can change port number at our convenience. This is particularly useful when a machine already runs a service using that port. And nothing prevents to deploy a same image in several containers, talking on different ports. That is also what makes the containerization ideal to deploy application. You can employ your complete working environment. File systems, network interfaces, ports. Everything will look and feel the same as in your initial environment. And thanks to mapping technique, it can be deployed anywhere and avoid potential conflicts. And the same kind of features is available to handle the file system seen from inside the container. We have the possibility to overload some part of the container file system with part of the host file system. Here, for example, the containers sees in /lib the actual /lib directory from the machine itself. This can be particularly useful to share input data, home directories or some driver libraries. As for network configuration, these choices are specific to each container. And Docker even makes possible to share a file system among the containers. We don't have enough time to dive deeper into details, but all this magic is possible thanks to two features of the Linux kernel present since 2008. Nominatively thanks to namespace that limits what a process can access. And the C groups would limit how much it can use. Let's talk now of a very successful implementation of this concept of containers, Docker. In reality, Docker was not the first technique settled. More than 40 years ago, the command chroot allowed to see a given directory as the root of a new environment. It was the beginning of file system masking and isolation. Afterwards, some products from Sun or IBM were aiming in the same direction, whereas isolation techniques were appearing in the Linux kernel. All these innovations made possible the creation of Docker Incorporated Company in 2010. In 2013, they delivered a light and very powerful solution that was adopted in many contexts and became a de facto standard for containers. But their great idea was to make available a repository where one could upload and publish their working containers already built. There exists now millions of them immediately available to all. Here is how it looks. For each image uploaded, developers can add a full documentation precise enough to configure them to their own needs just by pulling them, and setting a few environment variables when running the image as a container. This way of sharing images was so successful because not only were the images made available in the repository, but the way to build them incrementally was also downloadable as well. Let's illustrate how it exactly looks like. One describes all the steps required to build an image in a file named here docker.build file. First, one usually starts from an existing image whose name is appended to the keyword from. It is always the first step of any build. Then, after each order run, is stated a Unix command. It is the next action that needs to be executed for this build process. It could be installing a package, making a directory, modifying a configuration file. Any Unix command, in fact. This command is executed as root inside the container. At the end of a successful execution of each run command, a new layer is added to the container by Docker Builder. At this point the complete set of the container is saved. It contains the file system, and configuration of network in particular. And so on with as many layers as command. Another useful command is add and can be used to copy files from outside the container. As for a Git repository, each layer is uniquely identified by a checksum. This is also a great way to be sure that the image you are using has not been changed or corrupted before pulling it. This feature makes Docker secure and ideal to reproduce environment with enough confidence. Presenting all the building commands would take too much time. Let's just recall the command. From. Stating the initial image on the top of which we start building the new container. Run executing any Unix command and creating a new layer. Expose that publish a given network port making it reachable from outside the container. Volume that creates a file system proper to the container that can eventually be shared with other container. Add to copy files or directory from the host system to the file system of a given container. And user that change the current user inside a container. Let's now examine the classical cycle followed by a container and the images he's built upon or it generates. As illustrated in my initial example, the images are usually stored in a repository. hub.docker.com in the case of Docker. The command docker pull downloads an image and store it on the local machine as a copy immediately accessible. The same copy happens when processing the first line of a Docker build file. If an image given as argument of the from instruction is not locally present, it is downloaded from the repository and stored locally. Then, for every step of the build process, an incremented image is saved locally as well. Now comes the time to start a container with the command docker run. It consists in instantiating a container from the image locally available. An entire container environment is started, with its own file system, its own network permission. Inside this container you can run any command given as the last argument of the command docker run as the command ls illustrated it here. What happens is that the container is set up, and the concerned command is executed in this environment. Once completed, the whole container is not active anymore. An alternative consists in running docker run adding the parameter /d. D like daemon mode. In this case, the container is instantiated as before and runs either a default script which sees a part of the image, either the command given as parameter. But this time, the container remains active in the background, even when the given Unix command has completed. The ease of use of Docker also resides in a powerful feature. While a container runs, one can easily connect to it and starts additional process or modify the file system. At any point in time, via the docker commit command, one can decide to freeze this state in a new image that is saved locally. Then, thanks to the instructions shown here, this image can eventually be pushed in the repository, if one decides that it has any interest for the community. To end this introduction, let's see how Docker containers usage can be challenging on our current HPC resources. And in this context, Docker's magic might have trouble to operate fully, unfortunately. Do you remember the surprising fact I mentioned a few minutes ago when I was presenting the isolation of processes? Did you notice the process running as root? You may have also been bothered by the user command allowing to change the current user inside a container. You may have also noticed that this user is root by default from the very first line on a Docker build process. Unfortunately, what we can understand as a mandatory feature of Docker that allows to run any command to install any package inside a container, can also be a threat, a security breach on our shared HPC systems. Because, when it comes to Docker and HPC, three concerns remains. First, this root privilege is a big problem. As even if the container isolates the inside resources from outside, one can take the identity of any user and alter his file, for example, as he will have access to it. Second, an HPC system is highly optimized, whereas a container tends to be hardware agnostic, to remain the most portable possible. Third, in a context of open research, the license and business model of Docker Incorporated is not crystal clear yet, and it might be problematic to build on a technology that could become proprietary from a day to another. Luckily enough, some solutions are already existing as Shifter or Singularity. Developed with the idea to benefit from existing highly tuned library present on the system, they also cope with the root problem by running only as a user and ignoring any command in the build process of a container requiring root privilege. Just before leaving the floor to Mohsen, that will detail and demonstrate the Singularity solution in just a minute. Let me just point out these few references that may help you in your container journey. In particular, this excellent class on Docker by Brett Fisher, on Udemy and YouTube. And also these interesting articles. Let me also thank and give credit to the talented photographs of Unplash.com that illustrated this talk, and the voice of Brian UK from AWS Poly. As far as Shaheen is concerned, a lot of information can be found on our website. And here is our helpline. I am now available for any questions or remarks you may have.
Thanks, Sam. Wonderful intro. Any questions about this segment? We can hold on to the questions at the end as well if some things are not clearly constructed yet.
Yes, and feel free to send any question in the chat.
Yes, I would prefer to send it in the Q&A box. So Sam, you can take the charge of Q&A box.
Yes, yes.
While I'm talking. Thank you. Thanks, Sam. Right here. So Sam, you can see my screen, right?
Not yet, Mohsen.
Okay.
Yes.
Now it will be visible. Fantastic. So let's move on to HPC containers and specifically Singularity. So Singularity, as Sam mentioned, is containers for HPC, is a way of doing containers for HPC. It was first created by Lawrence Berkeley National Lab and was called as Singularity Lab. And then now it has been become a company called Scilabs, and there is a decent documentation and references on scilabs.io that you can follow if you wanted to. But primarily the motivation was for mobility of compute and making the experience reproducible without doing any effort onto different platforms, may it be supercomputers or laptops or cloud. It also is motivated by the development for HPC use cases, such as run as a regular user inside a container and can access shared file systems. So these are primarily the first hindrances for Docker to be deployed on a HPC system, which is a shared resource. And running as a regular user and be able to be able to access the shared file system will always give the system administration a sense of comfort that security is taken care of. Interpolation with Docker was really important from get-go. Singularity understood that because Docker is a very popular tool. People use it a lot. Docker interoperability is there, and you can use Docker images most of the time. You can always run the containers as background processes or services, which can then be used by the client processes to connect. We'll have a look at the example of that too. Singularity is supported on both Shaheen and Ibex as of today, and you can use it on our machines. So how do you access it? Simply load the module on Shaheen and Ibex, and you will see it in your environment. The command itself is called Singularity. Singularity command line interface is extensive. It has got quite a few utilities, but you don't need to learn all of them right from get-go to start with Singularity. There are few that are synonymous to the Docker users in terms of their work. So remember, Singularity is a platform, and it comes not only with container runtime, i.e., how to launch a container, but it gives you a method of building your own images and pushing them to repositories as well. So let's say build, exec, pull, run, shell. If you know these commands, basically these subcommands, these utilities, basically you are good enough to go forward in terms of running the containers on KSL platforms. We are going to demonstrate a few use cases, and all the use cases and the relevant Docker files are uploaded in GitHub, so you can access them whenever you want for your reference. Please let us know if there are some things that are not working. We'll try to modify them. So moving on to working with images, basically Sam has very nicely put forward a mind map of what images are and how to launch the containers. I'm going to go through, it can be a bit of a repetition, but probably a necessary one to make things more founded, more grounded. So basically an image is a standalone and immutable static file that contains the source, the application source, all the library dependencies required by that source during the runtime when it is going to run, all the tools, i.e. the code itself, the runtime, the system tools required to install stuff, the system libraries like libc, for instance, or libpng, for instance, or libjpeg, for instance, for that application to run, and user space libraries, the libraries that are the dependencies that you are going to install from source or from the package manager that are required by your application to run. I'll give you an example like MPI, for instance, or in GPU case, CUDA toolkit or CUDA libraries. Kublas and other things are going to sit in the user space as well. Settings, sometimes you need to set some environment variables, may it be for convenience or for configuration. You may want some configuration files to be in there. Your application may want it to run nicely as it should. So you can put those into. So these are going to be packaged, and effectively an image is a package format, which with all the ingredients that are required at runtime as packaged as one file. And it can contain manifest and metadata associated to it. And that manifest actually is the instruction about how it was created, the content that the image has, and execution instruction to the container platform, specifically the container runtime, which is going to launch the image into a container. Different image formats exist, and it started with every container platform had their own format, image format. So interoperability between two container platforms was not possible. Now, thanks to Docker, they were the first through the wall to adhere to a standard. Now, this is called Open Container Initiative, OCI standard, and the specification actually is for the image format as well as for the runtime format. So now different platforms are converging towards OCI specification for standardization. And moving on, we can actually see container image built with one platform, which can be used with another platform using the OCI interoperability. Images become containers once they are launched with container runtime. Docker Engine, Singularity, and Podman and Saurus are some examples of container platforms or container runtimes, which have container runtimes with them as well. So let's say for Docker Run, for instance, invokes the container runtime. In Singularity, we will see Singularity Run and Singularity Exit will do the same. And Podman and Saurus are a couple of other container platforms which we might get familiar with down in the future when they are mature enough. Multiple containers from the same image can be instantiated concurrently. So you can have multiple instances of the same application inside each isolated container running at the same time if you wanted to. As naming convention goes, images have two parts. The first part is the image name. The name, you can call it anything. It's up to your convenience. Then the other part is a colon separated part, and that is the tag, which is basically for provenance and for version control, and to allow people to understand the progression of the development of the image. These Docker images, which are very popular, they can be pushed, as Sam mentioned before, they can be pushed to public repositories or registries, as they are called, image registries as they are called. These container registries hold a plethora of images that you can work from, and they are a powerful way of sharing good work to the wider community. You can pull this image in Docker Hub using Singularity. So the first command that I'm going to introduce here is Singularity pull. And here, as you can see, that Singularity subcommand pull is expecting an argument of where to pull from and what to pull. So essentially, it is the first bit is Docker. So you're telling Singularity you need to pull image from Docker Hub. And in the Docker Hub, there will be a repository called KRCCL, for instance, in Coast case, and there will be an image. The image name is OSU OpenMPI 403, and then the tag is 563. What Singularity does is in pull is it's two functions. First, it is going to bring in all the sub images. If you remember Sam's Docker file, when it was building, every run command was creating an image, which may actually be called a blob here. And these OCI blobs are first gathered from the repository, and then they are converted into a single file. They're collapsed into a single file which Singularity can understand. That's called a SIF file, or Singularity image file. The reverse of this process is not possible. So you cannot convert a Docker image from a Singularity file at the moment. By convention, pull command will name the SIF image as image name underscore tag. So essentially, what I'm suggesting is the image name was OSU OpenMPI 403 :563, and the resultant file, if you don't give a name to it, is OSU OpenMPI underscore 563 SIF. This is a single static binary that can be run with Singularity. Another way to do the exactly same thing is using another subcommand called build, and build is going to take the same argument as where to pull from and what to pull, but you can rename the image as something else. So this is a mandatory thing, what to call the SIF file, and it will do exactly the same thing as we saw before. And I'll touch on this basically. Basically, if some of the sub images are already in your cache, they will be skipped to be downloaded. So basically, they will be the process will be a bit faster. So you can always pull from other places as well. There is another popular repository or registry where Singularity images can be pushed, and this is called Singularity Cloud. It's not free, but there is a free trial. So you can use up to 30 days, I guess. But the images will live there. There's an API key that you'll have to create to interact with Singularity Cloud. The instructions are on the Scilabs, and they are pretty nice in terms of following. But when you have done that and you can access that, basically instead of saying Docker here, we are saying library. We are calling it library, and that's the destination source. Sorry, from where you are going to pull. This is the repository. That's my username, and then the image and its tag. Once downloaded, basically it will again become a SIF file. You can always inspect what's in your SIF file. Sometimes it's not very useful, but at times it is useful if people have added attributes to the image for discovery. Docker has a similar thing. It's called Docker inspect. So is the command called in Singularity inspect. So if you have a SIF file, you can run inspect on it. If there is metadata, you will see the metadata. If not, then you will see the schema and the blobs. I'm pretty sure it will not reverberate anything relevant to you. But what it shows is when it was built, when the SIF file was built, what was the version, if at all, and then where it was bootstrapped from, or what is the underlying image that it was, and it has become the SIF file. So this was a Docker image from Docker Hub, and this was the repository where it got it from. This one is also important because Singularity is there are differences between Singularity 2 and Singularity 3. So the images that were built with Singularity 2 may have different characteristics while polling and running on interacting with Singularity 3. So it is also giving you some information about the SIF file, which Singularity version was used to pull the image. So in continuation, well, you can have a Singularity image which was built from a Singularity definition file, and we are going to see Singularity definition file in a few slides when we are building the image. We're talking about building the images. You can build the image in native format of Singularity right from scratch. In there, you can add attributes like author and version and some help on the images. And when you inspect such an image, this will show, like for instance, author, what version of this development was, and then other stuff is pretty much the same as we've seen before. It is showing me also that where it was bootstrapped from. So in this definition file, we were using an image, a base image that was coming from Docker Hub. So essentially, I was pulling the Ubuntu 18 image from Docker Hub and then building other stuff using Singularity on top of it. If the image builder has added some information about the image itself, you can always use run -help, and the SIF file name, and then it will spit out the description of the image if that is helpful. So now we move on to how to create our own image. We basically dealt with, in previous slides, we dealt with pre-existing images, pre-built images, either from Docker Hub or Singularity Cloud. Now we are going to say, well, I want to create my own. So you have two ways to do that, basically. One way is Docker route, and Sam has demonstrated that already. I'm going to go through it very quickly for completeness. And then we will go to Singularity route, how you can do this in Singularity using the Singularity definition file on KSL platforms. So in Docker route, first you will create a Docker image from a Docker file on your workstation. There is no Docker on Ibex or Shaheen, so you'll have to install it on your laptop or workstation, or you can do it in cloud or VM if you wanted to. Once you have done that, you'll upload that to Docker Hub in your repository, which is free. There is no charge for that, so you can use as much as you want. And then once that is done, you can now pull that using Singularity command, Singularity pull. You can pull that image on Shaheen or Ibex. If you are taking the Singularity route, remember that image will not work with Docker. So you are going to stick with Singularity as the container platform. And then basically what you're going to do is you're going to write the Singularity definition file, what to install in the image. You're going to build that image into a SIF file using Singularity --fake root. I'm going to demonstrate that. And then you can use that SIF file business as usual. So here is a Docker route. I'm revisiting what Sam has already shown. And basically what we start with is a base image. Here we are starting with an OpenMPI base image that we are providing from KSL in a KRCL library. And that's exactly what it is doing. Basically, it is saying, bring this base image as it is so I can start installing stuff. Those run commands and are appearing as steps, and these hashes are for each intermediate image after every step that gets created. At the end, it all gets collapsed into one image, and all the intermediate images are deleted, and then everything is collapsed into one image file that is a kind of an archive of all the intermediate images that are required. There is a very nice way of curtailing the size of that image when it gets explosively big sometimes, and that is called multi-stage build, but we are not going to cover it here. So once this Docker file is supposed to run, well, when you run it using Docker, you would do Docker build and then the Docker files path. This can be done, as I said, on your workstation, your laptop, or your cloud or VM. Once you have an image on your machine, now you have to push it in the registry, Docker Hub registry, in your repository. For that, Docker wants you to run the image as daemon, i.e. background process, and you can do that with -d, run -d, Docker run -d. This is happening all on your workstation, remember that. And then you want to commit your changes with some messages. And I am going to push this image into a repository called mshare with a name HPL and a tag 230. And I'm going to push that image, and then this actually gets to the repository stage by stage. Once that is done, remember this is an OCI image. As I mentioned, Docker's default format is now Open Container Initiative specification compliant. So this image, this OCI image, can now be read by Singularity platform on Shaheen and Ibex. So what I do is I go on my machine, my cluster, I load the Singularity module, I go to a home directory, and somewhere in the home directory, for larger images, it is advisable to export a Singularity temporary directory to, let's say, home, somewhere in home, and then run this Singularity pull command from Docker, from this repository, from Docker Hub, from this repository, and this image, please. And then it will pull the image as we have seen before in previous slides. So if you were supposed to do this same thing, but not with Docker, but with Singularity, you will need to write a Singularity definition file. You don't need to install Singularity on your workstation or laptop. You can do this on Ibex today, only on Ibex, not on Shaheen. So what you need to do is you can write a Singularity file which has two parts basically. The first part of the Singularity file is a header, and it encodes choice of operating system, the Linux distribution, core packages, the networking packages, for instance, and other important things that the OS image requires. Then comes the sections, and these are the image related changes that you're going to do on top of that base image that you have used. So here in the first bit of the Singularity file, definition file, you have got bootstrap. Bootstrap would point to the place from where the image is supposed to be brought. Docker means Docker Hub here, and from is the actual repository and the image that is supposed to be brought in, right? So that done, then you can go to add files from your host file system into the container. If there are some things that some files that are supposed to be copied from your host system to the containers file system, you can use this section called %files. Then anything and everything in terms of installing the dependencies, installing the source code, and so on and so forth can be done in this section called %post. So here I am doing apt-get on a few things. I'm downloading my source file, untarring it. I'm trying to build it, compile it, and basically all that is done in %post. I can set up the environment inside the container. Here I am exporting path variable and I'm setting a new variable called HPL home, which will only exist in my container when it gets instantiated. I can add labels, like for instance, I showed you, which will show up in Singularity Inspect. So basically, you can put in information like who was the author, what is the version, and you can always add help, i.e. how to run this, and some information about the image itself, extended information about the image itself. Once you have done that, then now is the time to build an image out of the Singularity definition file. And for that, ordinarily you would use Singularity build. Singularity build in its ordinary shape and form requires sudo access, but on IBEX we have got something enabled called fake root, which is going to let you build images in an unprivileged manner, only on IBEX compute nodes. This is important to say, only on IBEX compute nodes. So what you need to do is you need to first get a compute node using a salloc or salloc interactive session. You need to go to your home directory and set this xdg runtime directory to home and somewhere, so that Singularity, while building the images, can write these blobs, the intermediate images, somewhere which has space, because this is space or disk intensive process. And then basically module load Singularity there, and then you can do a Singularity build with this added argument called ---- fake root. The syntax is Singularity build ---- fake root, the name of the resulting file that you want it to be, and the path to the definition file that is there. Okay. Right. So you can do this in a job script as well if you don't want to do it interactively. So you will do exactly the same thing in a job script. Now you can run this image, and we are going to revisit this in the next section about how to run. But this image is ready, and you can run it with Singularity exec in a job script. But we are going to do this in detail in a few slides. Singularity cache, everything is cached in Singularity. There are some sub images that can be kept there, and those will be skipped if they are there. You can see what's in the cache using Singularity cache list command. So if you run out, or in this basically this cache is maintained in your home directory. It's a hidden file. It's a hidden directory tree called .singularity, and in .singularity/cache you have all these layers and blobs that you have previously downloaded or pulled from other places. You can always clean the cache or empty the cache if you are running out of the space. Singularity cache clean will help you there. It's a good practice to do this every now and then. So here we'll stop and maybe visit some questions from Q&A box, and then see if we have answers for that. And then we can take a 10-minute break here to take a breather. Okay, so I see Sabir has answered a few questions there.
Yeah, there was a question from Christos about accessing the GitHub repository, and we dumped the link in the chat box.
Okay.
That's yeah.
Cool, fantastic. Right, so let's, in the interest of time, can we subsidize the interval for 5 minutes rather than 10? I think we are going a bit slow. So let's convene at 10:35. Is that fine with you all? If that's fine with you all.
Yes, so Mohsen, just a minute. There was some question in the chat about Docker root test. And
Yes,
it's true that Docker root test is a very interesting thing. We, I tested it 6 months ago on my workstation, and it was not not completely mature, meaning that some part was working fine with some container image and some were failing. So Docker test is still in development, and of course we are watching it carefully, and it would be fantastic if it would work out of the box on, and it would be compatible with our system then.
most
But
definitely, most definitely, Sam. And Docker rootless, and there are other opportunities there in terms of other container platforms that are
yeah,
becoming more synonymous to Docker and have Docker-like experience. And we are also looking at that too. And these security concerns, they are not uncommon in other places as well, which are not that HPC-like, but are shared resources. So this is a common ground for a lot of use cases. Yes.
there was another question from Davey about the license of Docker, and of course it's open source, but um, the problem is to build it on something that will stay. And for me, what I meant in my talk is that we don't know about the business model of Docker. That's not crystal clear, and that's not a profitable company yet. So anything can happen. Of course, the source will stay open, but it can be closed anytime, and we will not benefit from the last version in the open source world then. So that's why we have to keep watching all alternative and very interesting one are popping now.
Yes.
That's what I meant.
All right. So let's start talking about, now we have an image. Now, how do we interact with this image to launch containers out of it? So you need a Singularity runtime for that. And to access the runtime, I'm going to tabulate some commands or show some commands. But some facts before going in. A container runtime instantiates a container from an image. So you have an image. When you want to run it, you use a container runtime. A container runtime runs an image, and remember these containers are ephemeral, so they are stateless. So once they finish, their state is gone. You cannot reproduce them from where they were. You cannot restore them from where they were. Whenever you reproduce them, they are starting from zero, from scratch. Um, HPC file systems that are mounted by default on Shaheen and IBEX are home directory, your project directory, and scratch directory, and the current working directory on Shaheen. And on IBEX, you will see home, scratch, and current working directory as your default mount points. You don't need to do anything. They will be mounted by default, and they will be accessible from your container to do the operations on the file system. By default, containers instantiated with Singularity are not writable. There is a way of writing files inside the container file system, but you can always write the files on these file systems because these are writable file systems. Because they have the same permissions, same ACL permissions that are transposed into the container as well. So you have write permissions on these file systems, but not on the container's own in native file system, right? Like /user /dev and so on. So okay, so launching interactive containers. So first thing that you can, first way of interacting with the image is to run a container as interactively. And this would mean that you are probably discovering the container or debugging or trying to understand where is what inside the container, so you can write up a job script for that, and so on and so forth. Uh, so and maybe looking at the environment as well. So what is the library path set to, and if there are other environment variables that are set. So here is an example of how to use it. You would run Singularity with subcommand shell and then the image name. What this does is it changes the prompt to Singularity, and now you are inside a container interactively. I here see what operating system I'm using, and at this moment I'm on Shaheen, which uses Cray Linux environment, generally speaking. But inside a container, I can see I'm using Ubuntu 18.04, which is weird, but basically that's the intended result, because this is a container with 18.04 on a Cray Linux machine, and other stuff. So a word on user management. So what happens to the user? Who is the user inside the container? What happens to, how does it become secure all of a sudden when you're using Singularity and Docker does things differently? Well, if you look at the who am I information on host, on the machine itself, I can see that I am my username, and my ID has this number on the host side. When I instantiate a container and run it, then run the Singularity shell on an image, and then run who am I, you can see I am still the same. So this is probably the most important security takeaway home message, that you are the same user as you were outside, which means to say all the permissions that are supposed to be on the host side for your username are replicated inside, and that is limiting your scope of doing anything on the file system and the system itself that you are running on, as your username allows you to. So dealing with the standard in and standard out of channels, basically it is exactly the same as you would do in general circumstances if you are running a bash line. Here I'm demonstrating that I'm piping. You can redirect input and output. You can pipe to and from a container. You can pipe from a container into another container. Here I'm exemplifying the last bit, which covers all of the above. Basically, I'm echoing hello, and I'm taking that hello word and then piping it to a container which is running an Alpine image, and echoing it into a file. And that also pipes it into another Singularity container, which runs world and pushes it into output. So eventually, what I'm expecting is my output.txt or out.txt in this matter will have hello world in it, and that's exactly what it has. So basically, you can run Singularity exec on different operations and processes and pipe them one after the other. This is a common thing to do in bioinformatics arena. To execute the container, you will run it as exec and run. You can see that these are two commands which sound synonymous. The only difference between the two commands is the exec runs the executes the command inside a container. You can invoke the command by prefixing with the image. So say for instance, Singularity exec the image name and the application name and the args. These application name and the args are important options to give in this command. Whereas if you have an image which has a run script inside it, and it knows where it is, it's an executable as on path, and it has what's called an entry point. For instance, in Dockerfile, it has an entry point, which means to say, make this image and put this line, so that when the image is instantiated as a container, this command runs automatically. And you can use Singularity run to achieve that. So if that image has that capability, you can use the Singularity run to achieve that. And this is where I am demonstrating it. So I have a Docker file, for instance. I am running, I'm pulling my base image Alpine, and then I'm saying, when you have pulled this, please run the command echo hello world. So when the container actually runs, it will simply run hello world inside the container. And this is exactly what is happening. I'm doing Singularity run and the image name, and it is automatically running hello world. As opposed to it, Singularity execute will expect the application to run and its arguments if they are required. Now, sometimes, yes, this is true that some of the file systems are by default mounted, but sometimes you want to bind mount other file systems as well, or other files or other directories. In such situations, you need to use --bind, or you need to set the variable Singularity bind to bind the source, and to bind the source, i.e. the directory path that you are trying to bind, to a directory path that will be the mount point inside the container. So this is optional, by the way, but you can always specify where to bind this this directory path that is on host into the container. Right? This can be multiple pairs, so you can have multiple paths bound to multiple places by a comma separated list. Here is an example. I'm trying to bind, for instance, this is IBEX compute nodes, and there are some AI reference data sets that are on compute nodes. They are never added by default into the container. So here I have a TensorFlow container, TensorFlow image. I'm containerizing the TensorFlow image, but I want the reference data set, for instance, to be accessible inside the container. I'm going to do --bind /local/reference, and this /local/reference will be available inside the container for being accessed by train.py. You can always launch background processes if you want to. If your application has components which are client server components, so you can launch this server component as a background process, or an instance as Singularity calls it, and then the client can talk to it too. So here in this case, we are exemplifying launch of a database, and we are binding some directories, and we are running a MySQL image, and calling MySQL application in it. We can check whether the instance has started or not. So yes, it has started with this PID, and then we can run this instance so that it gets activated. So it has started, but it has not started the database itself. It has instantiated, but it has not started the database itself. Once I run Singularity run on this instance, then it activates. Let's put it that way. After the Singularity run, my client application should be able to query this database. And here is a dump of all the commands on the server side, and the resulting activation of MySQL. And here is the connection from the client side, which is using this database. So for instance, as I mentioned, I'm using a MySQL image to start a database and instantiate it and then run it. And when I run it, basically I can run other commands inside that container as well. Like for instance, I'm trying to create a new user with some privileges inside the database, and it is spitting out some information about what is the username, what should be the password that needs to be used as the client from the client side. And here in the client side, I'm using again my SQL client to connect to that server that I just started, which is running in the background. And basically, as I can see, it has queried its version, and you can create new database entries if you wanted to. The example of this hopefully will show in demos as a real world example that we have been dealing with from the bioinformatics side. Now, as I mentioned before, the containers by default are not writable, especially when you are trying to do something with the file system that is inside the container, and there is containers native file system. You can't write on that. In order to do that, what we can do is we can instantiate the container as a sandbox, right? And what is a sandbox here? Basically, a sandbox is unrolling the image into a directory. So here I'm doing exactly that. So first thing that I will do is I'll call Singularity build with the option called ---- sandbox, and I'm going to give a name of my resulting directory right here. Here I'm calling it HPL and the image. So my image is residing here. What it will do is it will unroll the whole image into a local directory that I can see and navigate. So here I can see that a directory has been created called HPL. And if I do an ls on it, you can see that there's a root file system from the container, and it has been exposed here. I now can interact with this. I now can change or create files in this file system. To make things consistent, try using Singularity exec, and we'll show. You can use Singularity exec to create files. For demonstration that it is what it is, as I mentioned, I'm querying what operating system does this directory have, and I can access that it has Ubuntu. Here I am running a container from a sandbox. So say for instance you are trying to prototype or trying to see, or if the application tries to write some files in an standard location, like for instance /opt or somewhere. So you can actually run the container from a sandbox itself. So here I'm doing exactly that in a job script. So I'm running HPL on 16 processes. I load my environment, and then basically in my MPI run line, I have Singularity exec, the directory that has the container image and the application that is supposed to run that is inside the image. Once you have played with the sandbox, once you have done what you are supposed to do with the sandbox, i.e., let's say, for instance, you want to add a new file in it, you can create an image out of it, right? A SIF file back to normal, right? And you can do this by using Singularity build again. So here I am demonstrating exactly that. So what I'm saying is I want to put a new file in /opt of HPL directory. I touch that file, a new file .txt, and I build this image. So Singularity build -f is fake root, and then HPL new, the image name, and the directory. This is running on a compute node, by the way, of IBEX, because fake root cannot run anywhere else. And it builds an image called HPL new.sif. When I run the HPL new and see if the file is there with the new image, yes, it is there, right? So this is no more a sandbox. This is actual image now. So note that these changes will not be reproducible in when the image is rebuilt from a Singularity file. So say for instance, your original image hpl.sif was built by a Singularity definition file. These changes, the new inclusion of a file has not been added to that Singularity file automatically. So you'll have to do it manually. This was only done in a sandbox. So you need to take care of that provenance step, basically, to keep things consistent if you're using Singularity definition file. All right, so this brings us to demonstration of some use cases. And before going there, I have a few questions. Okay, so Ahmed is asking a question. Is there a way to checkpoint the Singularity container for jobs with a time limit on IBEX? Very, very good question. Your application and your checkpointing methods are always in the application, not in the container. And remember, the file systems are writable by default. The ones that are on this on IBEX, for instance, like Scratch or Home. You can always write your files in those, and they will be persistent because they are not associated to the container itself, right? So once you have written something in those file systems inside the container, they will exist outside the container. I hope this answers your question. And please let me know if it hasn't, we can revisit it as well. So Julian asks, when you bind a folder host image, does it persist when you exit the image? If the directory, again, the answer to that is if the directory resides inside Home or Scratch, for instance, which are native to the host file system, which are the file systems native to the host, yes, it will persist. But say, for instance, inside a container, if you're creating a directory in /10, no, it will not. It will not be persistent outside the container because it is containers file system. So any file system that is containers own file system, things will go away, right? And that's supposed to be like that. But if you want things to be persistent, please write it in home directory or /10. I hope I've answered your question. Right. So here in the first example, I am showing you an example of GROMACS. This is a computational chemistry molecular dynamics application. Basically, the Docker file that I'm showing you here is installing GROMACS on an OpenMPI base container that KAUST supercomputing lab has created, and I'm installing GROMACS 2020.04, right? I'm downloading it, I'm untarring it, I'm doing the CMake on it, and the stuff that usually we do. And I'm setting up some environment at the end, and that's a simple file. That's not really complicated. And to run that, basically, this is on Shaheen. Sorry, this is on IBEX. I'm running it on 32 processes with some steps before. So first thing I would do is I will set up my environment, i.e. I want OpenMPI from the host side to run it with MPI run. I want to export some variables like GROMACS use. So I'm going to prepend it with this prepending keyword called Singularity env. So anything prepended with Singularity env will be exposed as that variable inside the container. In this situation, Singularity env underscore GROMACS underscore use equals blank will be instantiated or will be set inside the container as GROMACS underscore use equals empty. Okay, And same is the case with this variable omp num threads. So if I wanted to set it to 1, I'll prepend it with Singularity env, and it will be set inside the container as 1. I'm pointing to some image here, and then I'm launching the image as expected. So here in the Singularity exec, which is prepended by MPI run, because this is an MPI application, I'm running the Singularity exec with the image name, and then gromax home slash bin slash gmx MPI and its arguments. So remember, this gromax home is slash user slash local slash gromax, which is native to the container. So if you remember, when installing, the gromax by default went into slash user slash local slash gromax, and that's exactly where I'm running from. That is inside the container. Here on Shaheen, I am doing some different steps, but ultimately the end goal is the same, running gromax from that container. I need to bind in order to run an MPI, in order to run an MPI in order to run an application which is MPI enabled inside a container. On Shaheen, I have to do a few extra steps and need to bind a few directories which are not by default bound. This mode of MPI is called bind mode, where I am not using the MPI from the container itself, but I am trying to use host MPI for performance sake, to use to run the application gromax inside the container. So the container application gromax will run, but when it is using MPI, it will use MPI from the host. So essentially, benchmarking Ibex and Shaheen, we've got similar results, pretty much similar results. In this situation, Ibex is a little bit faster because this is single node and these are new nodes compared to Shaheen. So on a larger run, obviously Shaheen will be much faster. Things can get complicated when you are doing complicated application installations, and you would not want to do them every time you are changing the platform. Let's say if you are moving from Ibex to Shaheen, or from Shaheen to cloud, or somewhere else, for instance, or other HPC clusters. You might want to install something on your laptop and would like it to run on Shaheen and Ibex as well. This might actually be one of the use cases too. So OpenFOAM is one of the application which is notoriously long in terms of building and complex in terms of what you need to add. When the developers have made it easy to build, but again, it's a very large application, takes 7 to 8 hours sometimes to build. So the Docker file actually looks not too different, but with more steps, let's put it that way. So I'm getting the base image, I'm installing some core utilities, including the dependency libraries. I'm bringing in the source for OpenFOAM and third party. And I'm setting up some variables which the build system recognizes and customizes the build accordingly. And then I try to build. When I have finished the build, which takes quite a long time, then I also set up some environment. Now, with Docker, there is a limitation that you cannot source the directory, source a file, a script, and keep the environment intact in the container. So essentially, in order to bypass that, so OpenFOAM actually OpenFOAM expects this bash RC to be activated so that all the environment variables that are supposed to be set are set. I am doing that manually in the Docker file. So this is exactly what I'm doing in the ends. When I'm setting the ends, I'm setting all the environment variables that are supposed to be set in the Docker file. By the way, I've curtailed that Docker file to fit in the slide. It's a long Docker file and it is available in the GitHub repository if you want to. On Shaheen, you would run this image with some additional things to do. So you will, this is an OpenMPI image. So you're going to load OpenMPI, load Singularity, and then set the environment variable like LD library path to have the Cray OpenMPI build, and also because you're overriding it, this will be overridden. This LD library path will be overridden. You'll have to re-establish all the paths that were set in the container. And then you're bind mounting some directories that are required to bind the host MPI. And then basically you run Singularity exec the bind mount minus B all that, and then the image, and then the application inside the container and its arguments, all prepended by MPI run. So we can help you out with running OpenFOAM inside the container if you're interested. But this is just a reminder that there are limitations at the moment that we have seen running these applications which are supposed to run on scale. So I am not saying that they cannot be tuned, but they out of the box may not perform as well as they were performing on native platform like Shaheen. So here native means I have installed OpenFOAM on Shaheen directly, and container means I have this container of OpenFOAM using OpenMPI, for instance, in this case. The versions of both are the same, and the problems that I'm solving are the same as well. The speed up I'm getting on native is far better, far superior, if you say. I'm getting up to 100x speed up for the same problem of strong scaling on 2048 nodes. It kind of plateaus after 512 for a container. So much so that, I mean, after 512, I don't see much huge benefit compared to the native, obviously. So might as well, after such scale, after those many cores, I might be using a native build rather than a container build. So this actually sets some expectations in terms of horses for courses, where you want to use container and where you would not probably use container in such situations. And this work was done by Dr. Rohuram. So deep learning training can also be done, obviously, in a container, in a containerized manner. You can write up a Docker file to, let's say here I'm writing up a Docker file to install all three popular frameworks: the PyTorch, TensorFlow, and MXNet, and also installing Horoward, and that's used for distributed deep learning training. So I'm starting with a container from NVIDIA, a CUDA container with cuDNN in it, and it is based off of Ubuntu 18.04. Okay, and I'm installing some core libraries. Then I install my OpenMPI because Horoward requires OpenMPI to do the distributed bit. Then I install my, then I set some environment and then start installing my Python. And here I am installing my Python with all the dependencies. For example, and I'm using pip to install, so I want to pip install. So I want to use the get pip to get the pip installer, the package manager. And also, in addition to that, I'm installing some core libraries like dependency libraries like Nickel to do the communication between GPUs. And finally, so before finally, I'm going to install the TensorFlow, Keras, PyTorch, and MXNet in my container. And last but not the least, Horvath. So basically, once I've installed my frameworks, I can then hook my frameworks with Horvath, and off I go using the Horvath. All that is available in GitHub repository if you wanted to look at. So once the container is ready, I can submit a job of single GPUs on Ibex using this container. So again, I have created this Docker file, and I have done all the development lifecycle of building an image using Docker, pushed it into Docker repository, pulled it using the Singularity pull, and now the image is on Ibex. And the image name is called Horvath GPU 0192.sif. Okay. So once I've done all that, now I can run the image. I'm using it on one GPU, one V100, and I load OpenMPI with CUDA 10, Singularity, and the invocation has one slight change now. With Singularity exec, I'm adding this --NV, which stands for NVIDIA, to enable expose basically the GPU stack inside the container, and run my Python train.py, or in this case, a PyTorch synthetic benchmark with the arguments. I run it and get almost the native performance that I would get on one GPU, that is around 354 images per second on a single GPU. I can do the same thing on multiple GPUs, fairly straightforward. So here I am doing the same example of Python benchmark on 8 GPUs, but on a single node. The performance is relatively higher. It's almost 8 times, more than 8 times. And I can actually scale out further. So what I can do is I can use multiple GPUs, but now on multiple nodes. So I might want to use, in this situation, I might want to use 16 GPUs. But here I'm using 8 GPUs, but 4 on each node. 4 on each node means there are 2 different nodes, 4 on each node. And I'm going to use the same command, but with different MPI run arguments of -NP equals 8, total of 8, but I want 4 on each node. I don't think I have the answer of this here, but I'll update my slides with the answer because the job kept on waiting in the queue because of the conference deadlines that are there. Ibex is very busy these days. So one other resource, one other registry, very important registry that the GPU users might be interested in is the NVIDIA's NGC, NVIDIA's cloud, GPU cloud registry. It has got tuned containers, and they are very regularly updated. They are not only for deep learning and machine learning, but they are computational chemistry, CFD containers that are there that you might want to look at. But they are for GPU usage, and you will need to generate an API key. It's a one-off step that you need to do to access the registry from your host machine to pull the containers from there. For that, first you need to have an account, and if you can follow the instructions on this link to generate that, that would be wonderful on your own. But if you want help with that, please let me know, and Sam know. We can help you out with that too. Once you have registered with the NGC registry to pull the images, you can easily pull the images as you were doing it from the Docker Hub. So here, basically, NVIDIA works very well with Docker using a prefix command called NVIDIA Docker. the images are probably hosted on a certain private part of Docker Hub as well. That's why Docker is there, but it has a suffix of nvcr.io. This is a private repository, and in that repository you have got the images. So you can actually go to the web and query the images from there as well. There are pull commands syntax. You can copy paste that from there to just replace these according to your need in terms of which container you want to download. So here I am downloading, let's say, Gromax 2020.2, and this container is not as small. So I am setting up this Singularity _ temp directory in my home directory, and basically this will allow all the temporary staging of the pull command to happen in the home directory. Once this image is on my system, I can run this image, the Gromax image, and solve the same problem that I was doing on CPUs on Shaheen on a GPU. And this actually took like 4 or 5 minutes to do the download of the image. And now I'm ready for the run for GPU Gromax. So I'm now using Gromax GPU. I'm setting up my environment on IBEX. This is IBEX again, and I'm trying to run it on 1v100. I'm going to export some variables. This image was expecting to source a few things. I can't source a few things in my image. As I had mentioned before, the entry points usually don't work that faithfully. The workaround to that is I set all the environments. Here I'm setting a CUDA home to my host CUDA. I'm binding it there, and basically setting up other directories which Gromax looks for. And here I launch the GMX binary with arguments onto the GPU in multiple steps. And this runs on a GPU because it has --NB on top. When comparing with the CPU runs on Shaheen, it took 0.317 hours per nanosecond for the simulation, 0.267 hours per nanosecond of the molecular dynamics simulation on IBEX. And when I ran it on GPU, it almost doubled. So basically, it does more. It is performing better on a GPU, single GPU, compared to IBEX 32 cores. So now I would request Sam to do a live demo on MySQL, how to launch it and how to launch LIMS for a bioinformatics use case. Sam, over to you.
Yes, thank you, Sam. Indeed, I will attempt to show you two demos, which are RStudio first, launched on IBEX, and also the LIMS example. Okay, so it's a work in progress, so hopefully it will work. Let me share my screen. Oh, before, do we have any question about one motion was mentioning, we're talking about?
Is this in a chat or?
No, but we don't have any. Let me see in the Q&A.
Yeah.
No, there are no question. So let's move on. Do you see my screen?
Yes, I can.
So here my goal is to provide you some example of running service in a container. And the first one I will demonstrate is how to run RStudio. So basically, we have been using a Singularity image of RStudio, and it has been quite straightforward to deploy it on Ibex, I should say, after fixing a few problems. So here I will just show you, drive you to the script a little bit to show you what we have to do to be able to dance our studio. So basically, my script has three parts. The first part is setting the environment variable, which putting the right path to reach our Singularity image, is setting up some path to access the editable and environment enable. And the second step is then to set a password and to prepare a session file, a temporary session file to a connection to our studio. Then we just have to run the studio from the Singularity image. And that's about it. So here I put I showed you the last step, which is the Singularity one. And basically, what I want to point out is what bandwidth the virtual will need to have. Because here, in SFV and in user, RStudio was dumping some temporary file. So we had to be sure that it was inside the container, managed inside the container, so that each container and Singularity copy could manage its own session. Okay. So let me make you a demo on how it can be launched. So here I've got my script and I will share it in the repository. And basically, I need to get a session on Ibex. So I will get an interactive session, but that can be done in a job. So hopefully we will get it. Well, Ibex is very busy. Maybe in the meantime, let me present the other example, which is an example with two containers based on Singularity. Basically, this is an example taken from a biology workflow, and that's an Inpsecting example. Basically, it involves Naga, actually, expert in biology could tell you more about this example, but what I point out is that we've got two components, basically. We've got the web interface, which is here, and the MySQL server, which is here. And the idea here is to launch these two services on two different containers, maybe on two different nodes. So the way we will do is we launch the Singularity MySQL server on one node, and then there's a tricky thing to do because we are not sure that the port is free on this node. So, and Singularity can map port. The MySQL server to talk on one football. So what we do in the script is we scan first the port available, and once it's available, we start the Singularity container. The other thing I would like to point out is that as we did for our studio, we need also to to set the password, and to set some directory variable here. So here basically I'm running the MySQL server in the container, publish the port, and then I'm run the container, the application container on another node on my base, and then make the connection. Okay, let me do the demo for RStudio. Okay, then I run the script. And you see here about some kind of dashboard where I can track and publish all the script, all the service I'm spawning on the node. And once the RStudio will start, I will be able to connect it. So you see here, if I take that node and go to the right port, I should be able to connect to my RStudio. Bear with me. Yes, I'm connected. So you see here, I launched the container based on the Singularity container on a node of my base, and then I can connect from my web server, from my browser. Okay, and that's the same idea for Lindsay. With the caveat, we have two different nodes running, the MySQL server on one side and the web server on the other. I can show you. I can connect to the. I launched it a few minutes ago, and I can connect to to the web interface. So that's about it. I'm apologize because it has been a bit shaky, but that's a work in progress, and we will publish the script and an automated way to be able to load it to the services. Is there any question or any remark?
Awesome, Sam. Right. So any questions about the microservice?
We are working on a framework that should make everything way easier. The dashboard I showed you is part of this environment, and basically the idea is that you will be able to launch services on either Ibex or Shine and to automatically publish some information live of about your service. For example, here, you see, here I've got the service automatically logged in my web server here, my dashboard, and so theoretically I should be able to connect automatically to these services. So we are working on making things more easy for you. That takes time.
Amazing. Right. On to best services, best practices, right?
Yes.
Cool. Thanks, Sam. I'm now going to move on to some best practices that we have jotted down. So essentially, the first thing that we have seen is when sourcing an environment script, it is not very easy to do it in Docker. So essentially, when you have done something and the application wants to set up the environment, Docker does not favor it very well because the environment doesn't, the shell doesn't live for that. And then when you go to the next instruction in the Docker file, it just goes away. Unless you're doing something in situ inside the container. So you can do this manually as done in OpenFOAM case, which I showed you before, setting up the environments on your own, and they will exist for the container in the image. When the container instantiates, that environment will be active for you to run any command after that. If bind mounting directories, like I did in the JavaScript, you will have to, because in path, you can append or prepend path to the existing container path. For LD library path, there is no prepend and append in Singularity at the moment. So you'll have to rewrite the whole path. And if you had some non-standard things in the path in the container, on LD library path, you'll have to add them again in your JavaScript so that they can be passed inside the container. Here is an example of OpenFOAM as I was pointing out. So here I have added a few things to LD library path. Now I am updating the LD library path, including the OpenFOAM third-party stuff that I already had in my Docker file. I have to do this again here because I have just overwritten the LD library path. Important thing to note is if your container is dealing with really primitive Linux kernels, that may actually cause problems running on a host with newer releases of kernels. So you can actually look at the release of a kernel inside or outside a container using uname -r and see if that is the case. If that is the case, do talk to us so that we can see if there are any alternatives to mitigate that issue. Singularity by default is read-only. Singularity container by default is read-only on the images and native file system. So you cannot read and write on the images native file system. On Shaheen and Ibex, as I mentioned before, there are a few file systems that are mounted, so they can be written on. If you want to write something on a container's native file system, you'll need to use Sandbox, Singularity Sandbox. For larger images to pull, you might want to do it on home, and you might want to export this Singularity temporary directory to somewhere in home directory to allow enough space for the Singularity pull command to bring all the blobs in and put them there. As another best practice, when building images with fake root on Ibex, always allocate a compute node interactively or in a job script, because a fake root will not work on login node. You will have a sub-UID error. That's a giveaway that you are working on login nodes. You need to export this XDG runtime directory to home and somewhere in home directory, so that temporary blobs can be constructed there and can be collapsed later into a single SIF file there. By default, Docker image blobs are cached into .singularity/cache in your home directory. You can always clean this cache space if it is being filled up, and sometimes your Singularity pull will break or crash in the middle with disk quota exceeded. That actually means that you have exceeded the amount of allocation on your home directory, and primarily if it is Singularity pull, then you might want to clean the cache before moving on and retrying. Ports are published by default on Singularity, so there is no way to actually expose more ports, because all the host ports are replicated or mapped on the same ports inside the container as well. So you need not to worry about forwarding the ports inside and outside the container. So there is no isolation on the ports. Bind mounting home can have some unintended implications in certain scenarios, like for instance in Python. Python packages are usually, user packages are usually installed in home. So if you are using Python inside a container, right, and it is expected that the Python installed packages inside the container are supposed to be used, then might as well use --contain option in your Singularity exec to contain the home as well, so that the home directory will not be mounted and the local home will only be dealt with inside the container, local to the container. That brings us almost to the end of our webinar. We are probably tracking well before we give the opportunity for more questions. We have some documentation that we are still developing, making it into a better shape, but all the nuts and bolts that are required are there. So please have a look and let us know if there are some things that are not working or breaking. We'll fix that. You can always email us on help@hpc.calc.edu.sa for Shaheen, and ibex@hpc for Ibex. And if you can please put containers in your subject line, then it will land with the right people, and then they will work on this ticket. Slides and recording will be shared with you in the follow-up email. I think slides are already up on the website. Recording we will edit and basically share via YouTube. Okay, so any questions or comments, please write up in your Q&A so that we can answer.